There we go. Okay, take two. We're starting a brand new unit. It's a brand new topic. It's called combinations, and it's the cousin of permutations. So today I need to talk to you a little bit to set up combinations and to understand combinations. We need to talk a little bit about sets and subsets, specifically some different definitions, and how to think and deal with sets and subsets in different ways, graphically, as a set. You'll see what I mean in a second. So a set is a collection of distinct objects. The objects are called elements or members of the set. The members of a set are listed in the following manner. So for example, this would be set A, and set A has 5 things in it. Those things are vowels. So it's the set of vowels, A, E, I, O, U. Set B looks like car companies or manufacturers, but only 4 of them. And set N looks like the set of natural numbers because it starts with 1 and not 0. So 1, 2, 3, 4. I can see that it goes dot, 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 meaning follow this pattern indefinitely. So infinitely all the way up to as high as you can count. 1, 2, 3, 4, dot, dot, dot. So often we're interested in the number of elements in a set. We use the notation NA to talk about the number of things in a set. So NA in this case, since we're talking about the set of vowels, that would be 5. There are 5 things in that set. Definitions. Definitions are, for this, some definitions for this I meant to say, are disjoint sets, 2 or more sets that have no elements in common, and I mean nothing in common. So for example, these two, there's nothing in common between B and A. They are disjoint for sure, right? I can't see any commonalities there. A subset, if all of the elements of set B are contained in set A, then B is said to be a subset of A. Here's how we write it. B is a subset of A. You know what this symbol kind of reminds me of, and I'm sure it reminds you of this too? It kind of reminds me of the less than or equal to sign. This is a less than or equal to sign. This is a subset sign. So it's kind of like a U on its side with that equal sign underneath. Subset means B could have everything in B is also in A, but there could be more things in A than B. There could be equal, or there could be more things in A than B. Intersection of sets. The intersection is where we look for common elements, common to both sets. And we talk about the intersection in 2 ways. Either we think of it as the things that are in A and B, or the things that are in A intersect B. This is the symbol for intersection, and it looks like an upside down U. So A intersect B really means what's common between A and B. The union of sets is really the things that are in anywhere between A, B, or both. It could be in both. It could be in just A. It could be in just B. And so we think of that as A or B. What are the things or what are the elements in A or B? This is the symbol for union is just a U. That's easy to remember, U for union. The other one, when we think of and, this kind of looks like an A, but missing the bar. So kind of that symbol, if you remember it as an A for and, then you'll remember it's an upside down U for intersect. Okay, let's try a couple examples using those definitions. So keep those in mind as we try example 1. Here we have 4 sets, A, B, C, D. There's different numbers in each set. In set A, what is NA? What would NA be equal to? And raise your hand. Hannah?
There are 20 elements.
There are 20 elements in set A. Good. So 20 there. What is NB equal to? Jerry?
Would it be 4?
Yep. There's 4 things there. And now that you got the idea, NC is 5. There's 5 elements in that list. And ND is 6, I believe. 1, 2, 3, 4, 5, 6. Yeah. Okay, so now that we know how, this is how we talk about how many things or how many elements there are in a set. I want you to name any disjoint sets now. Think about the definition of disjoint sets and then name for me what sets here might be disjoint, have nothing in common. What do you think, Yusuf?
B and C.
So we could say B and C are disjoint. Good. So B, C are disjoint. Part C, are there any subsets here? Are there any sets that you see that are part of another set? Ryan?
B is a subset of A.
B is a subset of A. Good. Because 2, 4, 6, 8 is definitely included in set A. But there are more things in set A. But B is definitely, all of B is included in set A. Good. Now we're going to find each of the following. So for D, I would like you to figure out what this new set would become. It's asking for A and C, which is similar to asking for A intersect C. So that's the same question. So A and C, what set would become of that? Now you have to practice your your curly Q bracket here. So set brackets look like this. It looks like an S and then a backwards S, right? With that little spike in the middle. So S and then a backwards S. Set notation or set bracket. And then what are the elements in A and C? What could I write? Yusuf?
You could write like 1, 2, 3, 4, 5, and then an ellipses, and then just to 25.
Now, unfortunately, the problem is set C starts at 5. So
Oh.
1, 2, 3, 4 are not common to both. We're looking for the common elements only. Okay. So think about what the common elements are. Jerry.
5, 10, 15, 20.
Yeah. So just not the 25, but 5, 10, those 4. Does that make sense? I hope. Okay. Let's go on to 5, 10, 15, and 20. So basically what it's asking is create a brand new set. This is another subset which represents A and C. So what's the common elements between A and C? And those are just those 4. Okay. You guys tried the next 2, please, on your own. A, what's this symbol mean again? What did we just say? A what?
Intersect.
Intersect D. And this is B intersect C.
Intersect.
Good. Okay. Everyone try those 2. See if you can come up with the elements that are in those 2 subsets. Yusuf?
Nathan Williams just wanted me to tell you that his Wi-Fi kind of just crapped out.
Oh, that's terrible. Okay. Well, good thing we're recording this then. Thank you. All right. A and D, who's got it? Hannah?
1, 4, 9, and 16.
Perfect. Because 25 and 36 are not in A, so we have to just deal with the ones that are common. What about B intersect C? B intersect C or B and C. What are the things in B and C? Is there anything in common between those 2, Charlie?
No, there's nothing.
That's right, because we already said that B and C are disjoint. Good. So if they're disjoint, there still is a subset here. It's just that we can't put anything in there. So here's the notation or the symbol that we use for what's called the empty set. So this is the empty or the null set. You may have heard it called the null set before. Okay. The empty set or the null set has set brackets, but with a 0 crossed out almost, right? That's the symbol for the empty set. And what all that means is it's not 0. It means that there's nothing in there. It's empty. Okay. Let's try B or C. Different question. When we ask for B or C, we're asking for the union of B or C. A union is a coming together of everything. So basically, when we're asking for this as a union, we could say it could have come from B, or there's the big or, it could have come from C, or it might have been from both. So let's list these in order, the way we see them, in numerical order in that case. So this starts with 2, because 2 is a part of B, then 4, then we jump over to 5, because that's the next in numerical order, then 6, 8, 10, 15, 20, and 25. So there's our new set representing the union, or B or C, the union of B or C. There's nothing in common, but if we put them together and stick them together as a union, there's a lot of terms that are in either or. What about C union D? C union D. Who wants to give that a shot? Jerry?
1, 4, 5, 9, 10, 15, 16, 20, 25. Would we write 25 twice?
Good question. What's the opinion out there?
I feel like we write it once.
Twice or once? Jerry, what do you think?
I would say once.
Once. Gavin?
Yeah, say once.
Once. Okay. Any other opinions? No other opinions? Yeah, you're right. You're both right. It is just once. It just happens in both. We don't have to write it twice to show that there's 2 of them. We just have to write it that it occurred, right? It occurred in either one. So 25 and then 36.
Yeah.
Good. Excellent. Okay, let's try the last example, but let's be smart about it. So A union B union C. I want you to think about what's in A, B, and C. Here's 1 to 20, 2, 4, 6, 8. Well, we already know that B is in A because it's a subset of A, right? So we don't have to worry about B at all, really, because it's a union. Union means coming together of everything. So we already accounted for B in A. What in C have we not accounted for yet in A? Just the 25, right? So 5, 10, 15, 20, that's all been accounted for in A. All we need to do then to answer this one off is to start a pattern. And that pattern has to have at least 3 numbers in it. 3 is the bare minimum for showing a pattern. 1, 2, 3, and that's the starting of set A, 1, 2, 3. Then we go ... meaning follow that pattern of increasing by 1 until you reach comma 20. So 1, 2, 3, comma until you reach 20. But then we have to add 1 more number in, and that's 25. So there's our answer to that one, just to make it a little smarter instead of writing all the numbers from 1 to 20. That's crazy. I know up here I wrote 1, 2, 3, 4, 5, but I wanted to include the 5 for other reasons. Okay, does that make sense to everyone? Any questions before we go on? Or can we leave that there and move on? Good? Okay. Awesome. So that's sort of your introduction into the world of sets. And now I want to show it to you graphically. And I'm sure that you've seen these probably in science class, or maybe not yet, but you will. We're going to talk about the graphical representation of a sets and subsets, and that is using Venn diagrams. Venn diagrams are a fantastic way of showing what each of those definitions look like in graphical form. So example 2, here we have disjoint sets and a good representation of disjoint sets. So here's set A, there's set B, with something brand new that we haven't seen yet. So I'm going to talk about that in just a second. This rectangle is like a superset. It's called the universal set, actually. And the universal set is kind of like the population. It's similar to, if you're thinking about stats, in stats, we talk about a sample and a population. Well, this universal set is sort of like the population. So, for example, let's say that this universal set represents all of the grade 12s at Blakelock. That's our population. But some of you are taking data, you'll be in set A, and other students are taking, I don't know, something else that you guys are not taking. Let's say these students in here are taking drama, and no one in here is taking drama, and no one in there is taking data. So there's no crossover at all, right? There's students in here, there's students in there. But the universal set is every grade 12. These two don't represent every grade 12. There are more grade 12s outside the circles, outside the sets, okay? But that's what disjoint looks like. Then we go on to intersecting sets, and it makes sense that they would have some overlap when they're intersecting, right? Because there has to be some common elements. So the common elements, which are the overlapping area of the two circles, I want you to shade the region of A intersect B in this Venn diagram. So we're talking about the region of intersection, and really we're just talking about the middle, right? All those things that would be in the middle. And there might be 5 students, there might be 10 students that take data and what did I say? Drama, right? They're taking both courses basically. Union of sets. The union is everything, right? It's putting all of A and all of B together. So if we were to shade A union B, what would I have to shade for this diagram to represent the union? Hannah?
Everything, like the entire 2 circles within, like also the middle?
Should I shade anything outside?
No.
No. Okay, so just the 2 circles. What about the middle part? Should I shade that?
Yes.
Is that included? Yes, it is. Good. So all of it gets shaded for a union because it's everything together. We're adding everything up, right? That's the OR. Here's what a subset looks like. A subset with 2 sets means B is included in A, but A may have more things than B. So maybe B has the numbers 1, 2, and 3. That's also in A, but A has 4, 5, 6, and 7 as well. So B is a subset of, okay? And finally, this picture, which is crazy, but it's an intersection of 3 sets now. The intersection of 3 sets would be the area represented by where? What area would be representing the intersection of all 3 of these, A, B, and C? Hannah?
The center, like the rounded triangle.
Yeah, right here. This middle part right there. That's where all 3 of them cross over each other. That's the intersection of all 3. So that's the common area where people are taking both data, drama, and music. Like let's say those are the 3 sets, right? These are people in the middle that are taking all 3 courses. These are people that are taking just data and music right here in the middle. These are people that are taking just data and drama right there, but not music, right? These people are only taking drama, and these people are only taking data, if those are our sets. So this is A intersect B intersect C, which is the dead middle, the area represented by the dead middle right there. The union of the 3 sets is represented by, what would I shade for the union? How would I shade the union here? Gavin?
Just the whole thing.
That is everything. Everything gets shaded because it's all of it coming together. Do I include the middle? Yes. Yes, we do. Oops, there we go. Going green, the whole thing gets shaded. Okay. Is this making sense to everybody, I hope? Any questions up to that point? Hope I'm not going too quickly or too slowly. Okay. So let's put this into action. Let's apply it to a question next. You've seen the Venn diagrams. You've seen what subsets are, the definitions of subsets. I know it's brand new, but let's try this question together, okay? In example 1, we have 12 students on the volleyball team. Let's call that set A. And we have 15 students on the basketball team. Let's call that set B. There are 5 students who play on both teams. Okay, so now we know that there's some duplication here. We're asked to draw a Venn diagram to illustrate these sets. So whenever you're asked to draw a Venn diagram to illustrate the situation, I always want you to start by including the universal set. So that's S. Always start by drawing a Venn diagram with a rectangle. You can't just draw the circles. You need something containing them, okay? This is the container. Okay, now I need 2 sets here, set A and set B. Here is set A. Here is set B. Basketball, volleyball. How many students are on both teams? 5? Okay. Well, where should this 5 belong on this Venn diagram? Where should we put that as a number, to represent the number of students on both teams? Hannah?
In the middle, like write a 5 in the middle.
Yeah, you can do anything you want. You could put 5 dots to represent the 5 people if you wanted. You could just write the number 5, but it's something to remind yourself that there's 5 people in that space, right? That's the important part. Okay, so there's 12 students on the volleyball team, right? So should I just put 12 right here then? Because this is A, that's the volleyball team. Should that be 12? Megan?
No, you're gonna use 7 because you have the 5 people in the common 2 teams.
So there's 5 people here that are also volleyball players. If we've accounted for 5, then really there's only 7 that belong in this section of A, because we need 12 students to fit total in this whole circle. Good. Since there's 15 people on the basketball team and we've accounted for 5, there must be 10 left over here as well. Perfect. So I want everyone to add up for me. What is 7 plus 5 plus 10 equal?
22. Oh, sorry.
Sorry. Yep. It doesn't matter. So that's 7 plus 5 plus 10 is 22 students. And so that means that in the universal set, if I was to ask you NS, right? What is the number in S in this situation? We would say that there are 22 students in the universal set. We're accounting for 22 athletes here. But when you add 15 plus 12 up, you get 27, right? 15 on the basketball team plus 12 on the volleyball team adds up to 27. Why? Why would that add up to 27 and not 22? Yusuf?
The 5 in the middle that you're like accounting for when you put in the 7 and the 10 are like removed from the total 27.
You got it. And so what you just did is explain the principle of inclusion and exclusion. By explaining that the 5 in the middle is double counted, we're just talking about what's called the principle of inclusion and exclusion. And I'm going to write that next. I'm going to come back to these 2 questions in just a second. So in general, for sets A and B, the number of elements in either A or B is the number in A union B, which is the 22 that we got up here, is equal to, add up all the ones in A. That would be the 12 students on the volleyball team. Add all the students on B, that's the 15 on the basketball team. And once we do that and we get our 27 from that, right? What do we have to exclude? These are the ones that we have to include. What do we have to exclude, Gavin?
The ones where A and B intersect.
Good. So the number in A intersect B. And there it is. That's the principle of inclusion and exclusion. You're going to use this formula a lot, and you're going to develop another one coming up for 3 sets in just a second. So explain what each of the following means. I want to know what it means and then give me a numerical answer. Actually, let's do the numerical answer first. So what is the number in A and B? What does that mean? And what's the answer? Ryan?
It's the number of people on both teams, so like where the two intersect, and that is 5.
Good. So the number on both teams. Love it. That's a great explanation. Okay. The number in A or B, what's that equal to, and what does it mean? In this situation, I should say. Charlie?
Is it the number on like either side, not including the intersection?
It's the number on either team. Could it include the intersection though?
Oh yeah, it can.
Yeah, it can. Because when we think about union, remember this Venn diagram here? When we think about union of sets, we're thinking about shading everything, including the middle. So that means that we're talking about 22 of them, not 27, but 22 of them, right? That's all 7 plus 5 plus 10 of them. And that is the number of people on either team. Good. Okay, any questions on that one? Everyone good? Pretty straightforward
Mr.
example.
Murray?
Yep.
When we get a question like this, like how are we supposed to assume that it doesn't mean when it says there's 5 who play on both teams?
Yep.
Like, what if it means there's 5 who play on both teams in addition to the 7 who exclusively play on one, or the 12 who exclusively play on one and 15 who exclusively play on the other?
I think you're overthinking it. When it says there are 5 students who play on both teams, it means that those 5 students play volleyball and basketball.
So you just took them from the total of the volleyball team, like, because it doesn't really matter where they come from?
Oh, I see what you're saying. Okay, now you're talking about this, aren't you?
Maybe. I don't know.
Yeah. Okay, let's think about how this applies back up here, right? If we have accounted for 12 plus 15 students, which is 27 students already, that's when I added the number in A and the number in B up. The problem with doing that, though, is that you've accounted for these 5 in the middle, not once for the volleyball, but twice for the basketball team. So in essence, you've double counted those 5 in the middle, the 5 that play on both teams, right? So the principle of inclusion and exclusion means we still want to attach those 5 somewhere. We can't have, you could either attach them onto the volleyball team or you could attach them to the basketball team, but you can't attach them to both. That's what we've done here by saying 12 plus 15. So that's why when we subtract 5 away, we end up with our actual total of 22, because we have to get rid of or exclude that extra double count. Does that make sense, Gavin?
Yeah.
Okay, Hannah.
I'm thinking about the same question as Gavin. It's like, how do you know like there are 5 students who play on both teams? Is 12 add 5, or like within the 12 students there are 5 students that also play on a basketball team?
I now I totally get what you're talking about, and I see that the question is not worded properly. So it should say, out of those students, 5 of them play on both teams, right? That's what that would be more specific, wouldn't it?
Wait, out of just the volleyball students?
No, out of all athletes, like out of these players, 5 of them play on both teams.
So couldn't like 2 of them come from the volleyball team and 3 from the basketball team? But it'd be the same math?
Oh, I see what you mean. But the problem is, even if you're talking about the 3 from the volleyball team, let's say, those 3 still play basketball as well. It's just that they play both sports, no matter how you divide them up. There's still a total of 5 students who play both sports. Does that make sense?
Yeah.
Yeah. So whether you say 1 and 4 or 2 and 3, it doesn't matter, because all 5 of them play both sports. That's the important thing I want you to take away from this. Okay. All right. So I see what you're saying, and I will try and make sure that that question is worded a little bit better. But basically what it means is there's 5 students out of the 12 and 15 that play on both. Okay. Let's go to this one, example 2. Let's see if we can figure out example 2 now. So there's 20 students in this class, let's say. If 15 of you take grade 12 English, 10 take history, and 3 take neither, how many take both grade 12 English and history? So I'd like you to see if you can figure that one out. Ella, I'll answer your question.
Do you mind just scrolling up a little bit? I didn't get to copy down the. Thank you.
There you go. So everybody try example 2. I'd like you to use a Venn diagram to help you figure it out, but you don't have to since we have this new formula for the inclusion and exclusion principle. We're assuming there's 20 students in this class. 15 of you take grade 12 English, 10 of you take grade 12 history, and 3 of you take neither of those. And the question is, how many take both grade 12 English and history? Jerry, do you have a question or an answer?
I'm kind of confused on how 15, 10, and 3 add up to 20.
They don't.
Oh, wait, no. Okay, never mind. I get what I thought it was
They're
10.
not supposed to.
My bad.
It's okay. They're not supposed to. Hannah, do you have a question or an answer?
Sort of an answer.
Okay.
So I basically like I first added the 15 and 10. Like these are the students that take class. And then I subtract 3 from 20 because there are 3 students that don't take any class.
Right.
And then like 15 plus 10, 25, 25 minus 7, and there are 8 students left. They're the students that taking both.
Yes, you're absolutely right. Now, I want you to
17.
use the principle of inclusion and exclusion. Use that, or draw a Venn diagram to help you explain that answer on your page, okay? But you're absolutely right. Sorry, I heard someone talking, but I didn't catch who it was.
Yeah, she said 17. Did you mean, sorry, you said 7. Did you mean 17?
She meant 17, yeah.
Okay.
Okay, so what Hannah was describing is this situation here, where we have students in the class, and that number, n of s, is equal to 20. Right away, I know I have to fit 20 students somewhere in this Venn diagram. There are 20 students, that's the population of this class. 20 people have to be fit somewhere in this Venn diagram. Now, I'm going to draw a set for grade 12 English. I'll call that E for English. I'm going to draw a set for grade 12 history, and I'll call that H for history. But I do not need to draw a set like this for neither, because if I do that, if I have some crossover, when you say 3 take neither, that has nothing to do with English and nothing to do with history. So there can't be any crossover. There couldn't be a third set here. If you thought that there was a third set, that's not right, because there can't be crossover between those 3, right? They can't share or can't be in history or English. What we could do, though, is have another separate set down here in the corner. That set is disjoint. It's disjoint from the other 2. And it's its own set that represents neither. So this set is actually called, and there's a name for it, this is called the complement. And we've heard that word before. We've seen that word before. When we're finding the complement of something, it means that it's the opposite or the inverse or the negative, right? It's the complement. So in this case, S complement represents the set, this disjoint set that has 3 people in it. Those are the 3 that belong in this class because they're part of the 20. They just don't belong in these two sets that we're dealing with right now. So we have to have a place to put them, and they belong in what's called the complementary or the complement set, and that is NS complement. This is an apostrophe, by the way, and whenever we see that symbol, that apostrophe, it means not. Okay? Not, or complement. Could someone please tell me, do we know how many fit in here in the middle? Students taking English and history, without Hannah's take on it. And I love that take, by the way. But Hannah, do we know right now, just looking at this, how many are in the middle?
Yeah, you have to calculate it. It's
You have to calculate it, don't you? Like back up here, we knew it told us there's 5 students who play on both teams. So we knew exactly what number to start with here, right? So Hannah did the calculations for us, and we're going to go through that again right now. She said that I'm going to use this principle to help me figure out how many are on A and B, the number in A and B, right? And using the inclusion exclusion principle, here's what we know. We know that if there's 20 people in this class, but 3 of them are not taking either of these two, then the number of people we have to account for in this circle is 17. So the number in A union B, or in this case, E union H, is 17. I'm going to write it as 20 minus 3, which is really 17. I know I have to account for 17 people in these 3 bubbles, right? In these 3 sets, or 2 sets, but 3 sections of the sets, I should say. NA is how many students are taking grade 12 English. That's 15. NB is 10. And the number in A and B is the thing we're trying to find. Well, guess what? We have a formula now. We can solve for that. I'm just going to do some switcheroos, a little bit of algebra. This is minus. Let's move it to the other side. Becomes positive. Number in A and B is equal to 15 plus 10 minus 17 then. Right? We're taking this 17, we're moving it to the right side, and that's 8. Just as Hannah suggested, it's 8. So what you've done, Hannah, is use what's called the principle of inclusion and exclusion to help you figure that out, that 8 out. But you're using this formula, and I wanted to show you that, how you're using that formula, okay? Perfect. So now that we have the middle is 8, we can figure out the rest. How many students in this class are just taking English, only English, but not history? Charlie?
Would it be 7?
It is, because 7 plus 8 adds up to our 15 that are taking grade 12 English. Good. And how many are just taking history only? Only history? Ella?
4.
Not 4.
Oh, sorry. 2.
2, right, because there's 10 that take history, but 8 are accounted for here. So 2 more. 8 plus 2 makes our 10. Perfect. Now, if you want to double check to see if you have this all right, all you need to do is add up 7 plus 8 plus 2 plus 3. If you add those up, you should get your sample, or your population, I mean, of 20. And it does. That adds up to 20. Okay? So how many take both grade 12 and English and history? Therefore, you didn't really have to do this. I just wanted to show you that as an aside, right? The 7 and the 2. Therefore, 8 students take both. Does that make sense? Is there any questions on that one before I move on? Let me know if there's any questions. I'll give you a second to copy too if there's people copying. Hannah?
So when we're asking, now answering the question, do we have to write the diagram, or we can just write the formula and then figure out the answer?
You can just use the formula. You can just, well, actually, that's why I asked you, could we use this Venn diagram to solve this? Right? That was my question originally. I said to you, can we just based on this question, do we know that middle is 8?
Nope.
So there's no way you could solve this with the Venn diagram then, really, right? You had to calculate it using this formula or your formula, but the inclusion and exclusion formula to get that 8 first. And once you know what the 8 is, then you can fill out the rest of the Venn diagram. But you don't really need the Venn diagram for that.
Okay, and then
So this
yeah.
is what I would give you marks for, just this.
Okay.
Make sense?
Yep. And for the A union B, do we have to write it as a separate step, or we can just include it in like what you wrote?
Just
like,
include it.
Okay.
Yeah. Okay. So you don't even need that first step if you don't want to. You could write it like this, and I know exactly what you're talking about, right? From that line down. Okay. Any questions on that? Everyone good now? Yay, nay? Yes, no, maybe so? Okay. All righty. We're going on to the mega question then. Counting with Venn diagrams. This is the principle of inclusion and exclusion I give you with 3 sets now. In example 3, we have a Venn diagram shown down here with 1, 2, 3 sets, and we're going to use it to help solve this question. According to a representative of student services, of 100 students currently taking grade 12 courses, so automatically I know that there's 100 students that have to fit in here somewhere. I'm going to write NS equals 100. That's for my brain to remember, right, I need 100 people that fit somewhere in here. There cannot be any more than 100, basically, is what that means. Out of those 100 students, the distribution of students in math courses is as follows. So it looks like there's a lot of information given here, but I don't like the way it's given, so I'm going to rewrite this information, but using set notation down here. So I'm going to call it, well, we got calculus and vectors. Let's call that set C. So the number in calculus is equal to 52. Functions we'll call set F. So number in functions, that's 38. So this is just me organizing my thinking around what the question's asking, or what it's telling me, I mean. In data management, we'll call that set D. In data management, we have 41. And so there's calculus, functions, and data. There they are. But then it gives us more information, functions and data. Okay, so that represents the number in functions and data. That's the intersection, is 17. The number in functions and calculus and functions is 22. And the number in data and calculus is equal to 15. So there's me thinking about that, right? The last thing it says is there are 8 students taking all 3 courses. So we can write that as the number in calculus and functions and data, all 3, is equal to 8. Okay, so far so good. We're just organizing our thinking around this question. We've got it all organized here. I'd like to know, well, first of all, we should label our Venn diagram. So this is going to be calculus, this will be functions, and this will be data, let's say. Doesn't really matter though. Where do you think we should start? If we're going to fill out a Venn diagram or draw a Venn diagram, where should we start here, Ryan?
The center.
Absolutely the center. In this center, we have this exactly. Calculus and functions and data, there's 8. So we're going to start with 8 in the middle. That's a great, great, great place to start. Okay, what should we do next? How else should we fill this out? Gavin?
Now, for all the ones that have 2, like F and D, C and F, D and C, subtract 8 from all of those and then put those in their respective intersection boxes.
Good. These are all representing the intersection between 2 sets, 2 circles, right? So if this is all of the students who are taking calculus and data, then calculus and data, there's 15 students, right? So we need to have 15 students accounted for here. We already have 8 accounted for, so we need 7 more to fit here. All together, 7 plus 8 adds up to our 15 total. Gavin, perfect. Let's go on. Functions and data, that was 17. So 17 minus 8 is 9. And calculus and functions was 22. 22 minus 8 is 14, I believe. Is that good? So what we've done is taken each of these, just as Gavin mentioned, all the doubles or the overlaps, the intersections between these two, each of these two, I should say, and we've subtracted 8 from each of them. Okay, next. So what we're doing basically is we're working our way from the inside out, right? That's the strategy here. We work from the inside out. How many students in this, what first of all, what does this represent right here, this section of calculus? Charlie?
That would be students that only take calculus.
Good. And how many students are there that only take calculus?
52.
There's 52 students total taking calculus. You're right. But look at all of these. These numbers are still inside that circle of calculus, right? That set. So haven't we already accounted for these?
Yeah. Would we have to subtract 7, 8, and 14 from 52?
You got it. So the answer here is actually only 23. There's 23 students that only take calculus. That's what this section represents. Okay? So we're still using the same strategy. We're still subtracting the numbers that we've accounted for already. Let's look at functions next. There's 38 total people that have to fit inside this circle somewhere. But look, we've already accounted for 14, 8, and 9 of them. So 38 minus 14 minus 8 minus 9 is 7. Taya.
I was just going to answer that.
Okay, give me the data one now.
17.
There's 17. Tell me why.
If you take 7, 8, and 9 away from 41, that's what you get.
You got it. There you go. There's your Venn diagram filled out. Perfect. Hannah. Hannah,
Oh,
what's your question?
sorry, I just calculated wrong.
Oh, are you okay now then?
Yep.
Can everyone confirm that these are correct? I don't know. I'm assuming that these are correct. Everyone good? I mean, I did.
Yeah, they're correct.
Yeah. Okay. So we have a backup there. Okay. So we have our Venn diagram filled out correctly. In question B, it says, how many study only functions? What's the answer to that? Jerry?
23.
Only functions.
Oh, my bad. I read it wrong. 7.
There's 7. Study. Only functions. Good. That's the number that we just talked about up here in the corner, right? The 7 that only are taking functions. I'm going to ask you another question, actually. How many students, out of this Venn diagram, how many students are taking calculus or data? So that's calculus or data, but not functions. How many students are taking calculus or data, but not functions? I'm just writing the question down. So how many are taking calculus or data, but not functions? What do you think? Charlie?
I'm not totally sure if this is right, but would it be 23 plus 7 plus 17?
Why?
Because you have to add all the students just taking calculus, all the students taking both calculus and data, and then all the students taking just data.
Yeah, they count too. So the 23 count, this 17 count, but so does this 7. They're taking calculus or data, and they're not taking functions, right? Basically, you want to take away all of these. You don't need any of these because they're all taking functions. Good. Okay. Next question. How many students are taking math courses at the grade 12 level? How would we answer that? Yusuf?
Would you just add all of the numbers in the middle?
You
Or
got it.
like in the whole thing?
In the whole thing. That's an
And
or
that's 85 students.
85. So we have a total of 23 plus 7 plus 17 plus another 7 plus 8 plus 9 plus 14. And that adds up to, wait a minute, it only adds up to 85 students. Didn't it say that there's 100 students currently taking grade 12 courses? Uh-oh. What does that mean? Or what does that imply? Ryan?
That 15 are not taking math.
And we call that the number in the complement, or S complement. That is 15. So we can write that down here. S complement is equal to 15. There must be 15 students not taking any grade 12 math courses right now. Good. Okay, I have a feeling that Hannah and Gavin had their hands up from before. Is that true?
Yep.
Okay. So lower all. Or Gavin, did you have a question?
Oh, no, I just kind of had my hand up for all of those.
Okay, so here's what we have. And you saw from before what the principle of inclusion and exclusion looked like for 2 sets. I would like you now to come up with the principle of inclusion and exclusion for 3 sets. Here's what I mean. There is another way to get this 85 number. That's a very important number because it represents the number in this or that. That's what that 85 represents. We don't have to fill this Venn diagram out. We could get it using a formula. That formula involves these numbers here. So what I would like you to do now is to figure out how to get 85 out of these numbers here. Some you'll have to include, some you'll have to exclude. That's why it's called the principle of inclusion and exclusion. So I'm asking you to figure out what is the number in A, union B, union C in general equal to when we have all of these numbers. Okay? Try it right now. Jerry, question or answer?
It's a question.
Okay, go for it.
Where did you get 15 from?
15 comes from if there's 85 students accounted for inside these sets, then there's 85 students taking math at the grade 12 level. But up here it says, remember that's why we wrote the 100 up here? There's 100 students taking grade 12 courses. Not math courses, just grade 12 courses. So if that's our population, if that's our universal set, then that automatically implies that there must be 15 down here that are not taking any math courses right now.
Oh, okay.
Right?
Thank you.
It's this 100, take away that 85.
Okay, thanks.
Okay. Hannah, do you have a question or an answer?
I thought I have an answer, but then like I figure out something wrong with it.
Okay, keep working then. Keep working away at it. See if you can find the principle of inclusion and exclusion using those numbers. Yusuf, question or answer?
Answer?
Okay.
Should I just like say it?
Yeah, I've given you enough time. Sure, why not?
Okay. So I think the answer is the union of A, B, and C is the number of A plus the number of B plus the number of C minus the number of A intersection B minus the number of B intersection C minus the number of C intersection A.
Okay. And what do you get when you do that? When you added these 3 up and subtracted those 3?
I haven't tried it yet. It was just theory.
Good theory, but it's not 85. Close, but it's not 85. Megan?
Do you have to add at the end plus the number of A intersection C intersection B? That's the 8.
Got to add that back in, right? Good. So that was Yusef. We were so close. Let's write it out. It's A, B, and C, all those numbers together, but then we exclude this set, the number in A and B, minus the number in A and C. Guess I'll do here, minus the number in B and C. So far, so good. So it looks like we've added 3 in. And that would be these 3. We've added these 3 together. Then we excluded the next group of 3. We took them away. But then we included again this group of 8, that 8 at the end. So I want you to really think hard about why, and that does give you 85, by the way. So this is include. This is exclude. And this is include again. I want you to really think hard about why that happens and why that works. And really important to think about this 8 in the middle. When you're including 52, 38, and 41, how many times have you included that group of 8 out of those 3 groups there? Anna?
I think for like the reason why you have to include the 8 in the end is because when you subtract the intersection of either 2, you are taking away 8 3 times, but like you cannot take away entirely, so you have to add 1 back.
That's right. You can't just say we're forgetting about those 8 in the middle, can you? So when I'm including all 3 sets here, have I included that 8 in the middle? Have I included it here in the 52? Yes. Have I included it here in the 38? Yes, right? Because that 8's part of the functions group. Have I included it here in the 41? Yes, that's part of the data group too, right? So I've included 8 3 times. That means I triple counted it, right? I don't want to triple count it. That is including that number in the middle too many times. When I get rid of the duplicates here, 17, 22, and 15, let's start with the 17 in functions and data. See this 8 plus 9? That's adding up to 17. But when I get rid of 17, haven't I gotten rid of the 8 once here? 22 means I've gotten rid of the 8 twice from this group. 15 means I've gotten rid of the 8 3 times now from that group. So even though I included 8 3 times here, I excluded it 3 times there. So we've included and excluded 8 an even number of times. It's canceled out. So if we just stop there and say that's our answer, we haven't actually included that group of 8 yet. So at the end, we have to include it back in again. Okay. Megan, I think that's just a hand from before, or is it a question now?
It is. Sorry, I forgot.
And Gavin, question?
Yeah, I did it a different way.
Okay, how'd you do it?
So what I did is I added A and B and C, like the whole circle. So the 52 plus 38 plus 41. And then I subtracted the areas where it overlaps rather than the areas where it's like exclusive. So I subtracted 14 because that C and F overlap there. And then I subtracted the 9 because the F and the D overlap there. And then I subtracted 7 because C and D overlap there. And then now they've all overlapped and converged on the middle point like 3 times. So I have to subtract the 8 twice.
Ooh, interesting. So although I absolutely love what you just did, and that may come in handy for an assignment later, by the way, hint, hint, that method works perfectly if you've done a Venn diagram, if you know what these numbers are. So you could always calculate them too, just by subtracting, right? 17 minus 8, and I get that. But if you don't have the Venn diagram at all, and you only have the numbers from the question, then using this principle of inclusion and exclusion, I think it just eliminates that extra step. Does that make sense? So I did it first on purpose because I wanted you to see these numbers. That's an important thing to me, that you saw these numbers. But what if you didn't do that? What if you didn't need to do a Venn diagram? What if you just were asked to use the formula? Then I think you'd probably just want to go with this, add them up, that, subtract, and one more add. Now, with that said though, and this was a big hint, I love that method because you can use that method to solve for different things in this Venn diagram, different sections, I should say. Okay? So, awesome job. Oh, I forgot to put that extra bit in, so make sure you include it yourself. It's NA, NB, NC minus the double, minus the double, minus the double, but then make sure you add in A and B and C. And keep in mind Gavin's method. I'll call it Gavin's method. For future use, I want you to, if you need to, you could write that down, how he did that, and the fact that he had to exclude the 8 twice and not add it back in at the end, right? That's an important part of that method. Ella?
Do you mind explaining again just why we had to subtract the 8 twice?
Gavin?
Yeah, so basically when you put down each circle, so when you put down the C circle, you're counting everything inside of it. And when you put down the F circle, you have to exclude the 14 and the 8 because they both overlap there. And then when you put down the D circle, you have to exclude the 7 and the 9 because it overlaps with the C and F respectively. And then you also have to exclude the 8 again because it overlaps with an area that's already like that same area again.
Okay, thank you.
There you go. Perfect. All right. That's that. Let's see, what time is it? We're going to take a quick 10-minute break. Everyone get up and stretch for 10 minutes, and when we come back, if you haven't done so already, you don't have to print these off at all. I want to do some of these practice questions with you on shading Venn diagrams. These are, I moved them. They were on Friday. I now have moved them up to today. So if you didn't see them before, that's why. They're just sort of like, they just got moved. So if you want to, you can print them out during the break. If you don't want to print them out, that's fine. We're only going to do a couple of them anyways, and then the rest are for practice, okay? So this is something you can get printed out in the meantime if you want. I'll see you back at 2:10 p.m. Oops.
Mr. Murray, there's Venn 2